So welcome to my next webinar in my series on modern Java by example. Today, we're going to turn our focus back to the Java Completable Futures framework. And we're going to look at a very interesting set of methods that test all kinds of interesting advanced features of the Java Completable Futures framework. This example is actually quite similar to the example we looked at the other day relating to the use of the Reactor framework to do much of the same computations. But as you'll see momentarily, the Java Completable Futures framework has a more interesting set of features with respect to asynchronous computations than Project Reactor. So it'll be fun to compare and contrast the different approaches. So with that, let me go ahead and share my screen, and we will be off to the races. So as always, you can find the code I'm talking about here in my live lessons GitHub repository. This happens to be in the Java 8 folder, even though it's more than just Java 8. And if you look down here, there's a directory that's called EX8. So if you click on that, you'll find all the source code that we're about to walk through. So without any further ado, let's go over and look at the source code. So again, this project is structured very similarly to the one we looked at the other day that was done using a Project Reactor. In fact, we have some of the same abstractions, but naturally they're implemented using completable future features. So let's first go ahead and take a look at the main program. This has a count of the number of fractions we're going to use with our larger multiply operations that come a bit later. So we have 10 of them. And as you see, these are very large fractions. And so they're going to take a while to compute. So we're going to need to do them asynchronously, and we're going to need to do them with a pool of threads, excuse me. And you can also see down here, we've got a bunch of strings that represent various big fractions, either big fractions or numerators and denominators for fractions. Those will get used as well. Down here, we're going to have a field called sCompleted, which is going to be a completed future to null. And that's similar to a void mono or an empty mono, if you will, that we talked about with Project Reactor. And we use this to represent a completed computation. And you'll see how it gets worked into the flow of control when we look at the example methods. We also have some other fields that are very similar to what we looked at the other day. We have something called a big reduced fraction, which is a big fraction that takes a big integer as the numerator and a big integer as the denominator and makes a reduced fraction from that. And then we also have something called big reduced fraction future, which is a completed future to this big reduced fraction. And that also turns out to be handy in some situations when we want to do various types of arithmetic operations on the big fractions. The reason I choose to use big fractions, by the way, is that they're computationally intensive to do operations on, especially large ones. So let's take a look at the main program. The main program is going to go ahead and register a whole bunch of method references, and these are going to be treated as suppliers in the context of something called the async tester class. This is a utility class that we used for the Project Reactor as well, although the implementation is ever so different. And what we're going to do with the async tester is we're going to go ahead and register a bunch of suppliers. So we have a list of suppliers. And then after everything's been registered, we're going to go ahead and kick off everything to run asynchronously. So you can see there's actually quite a number of asynchronous computations to perform here. In fact, more than we did for the Project Reactor code the other day. And the reason that we have more code this time is that we're going to want to do it in a way that can use more advanced features that we have for asynchronous, for the asynchronous support with completable futures. So there's more things we can do with a completable future than we could do with the Project Reactor monos. So you'll see how that plays out here in a second. Down at the bottom, after we register all these suppliers, we then go ahead and run the tests. We'll look at that code in a second. And then the join method is what will wait for everything to finish running. Let's just go ahead and take a look at the register method real quick. This is register in the async tester. Very similar design to our implementation yesterday. The main difference being that yesterday we had a list of suppliers to monos that were void, and today we have a list of suppliers to completable futures that are void. But they play very, very similar roles. And the main difference is, again, that the completable futures have a bit more expressivity with respect to the asynchronous computations that they can provide and perform. whereas the monos are a bit more limited. And you'll see how that plays out when we look at the code in a second. The register method just goes ahead and takes a supplier and adds it to the list. And then the run test method converts the list of suppliers to completable futures to void into a stream of suppliers to completable future to void. We then go ahead and use the map intermediate operation from the streams framework to go ahead and call all the get methods on the suppliers, which will then trigger all the tests to run asynchronously. And then we use our typical collect method with the collect to future feature, which under the hood, as you may imagine, uses our futures collector. So futures collector is going to take a stream of completable futures, the objects of type T, and store them intermediately in a list of completable futures to objects of type T, and then ultimately produce a completable future to a list of objects of type T. And we've looked at all this code many times before. It uses the very clever allOf technique. The approach, we also looked at an approach yesterday that did something similar for monos, but we're not going to need that today, of course, because we're doing completable futures. Okay, so let's kind of pop back up here. So that's how everything gets set up and run. And oh, I should do one more little thing real quick. The async tester, when we're done getting back the single future that waits for all the other futures, when that finally triggers, the thenAccept method is called, and we print out how many tests were actually completed. And you'll notice that thenAccept returns, that's the return value from run test. So that comes back as a completable future to void, and then our main program simply joins on that. So again, very, very similar to the monos we talked about for Project Reactor. Let's start taking a look at some of the methods, though, and you'll start to see the differences between completable future and the Project Reactor monos very quickly. So the first method we're going to look at is called test fraction reduce. If you recall, yesterday, the test fraction reduce that we used first was done entirely synchronously. So it actually ran in the main thread of control. And just for kicks, let's go ahead and run this code so you'll get to see where everything ends up executing. And I'll let it run, and then we'll come back and look at it later. And so you'll see that it does more or less the same kinds of things that the test did yesterday. There's a few more tests that we have here because we can do more things with completable futures than with Project Reactor. But basically, this goes ahead and runs a lot of computations here. Okay, so with that in mind, let's go ahead and pop back out of here, and we'll see that test fraction reduction is going to go ahead and create a bifraction that will be a big fraction that's unreduced. We're then going to have a supplier called reduce fraction that, as the name implies, is going to go ahead and reduce that fraction. And it does it basically by calling the big fraction reduce method on the unreduced fraction, which takes a while to run. So we're going to run it in the background, obviously. And then we have another function called convert to mixed result, which converts the reduced big fraction to a mixed fraction. And then finally, we have a consumer that will print the results. These, again, are very similar to what we saw with the approach yesterday with Project Reactor, but they can use different methods because the completable futures API is slightly more expressive. So here's how things start. We're going to go ahead and say completable future supply async. And this is where things quickly diverge from the original use we did yesterday with Project Reactor. There, we were able to use the just method, and so that would go ahead and emit in the calling thread. Whereas with completable futures, you're always going to be starting them running in a thread in the background. So when you do supply async, that takes you into the completable future framework implementation, and what it does is it takes this supplier and it registers it to run in one of the threads in the common fork join pool. You can also give your own pool, of course, here as well, much like you can do with Project Reactor or RxJava. When supply async finishes doing the fraction reduction, what it'll do is it will then call the next method in the chain here. So this is basically a chain of so-called completion stage methods. And what they're going to do in this case is it's going to take the result of reducing the fraction and then convert it to a mixed string. And then apply is a method that is really intended for synchronous short-lived calls. So obviously converting to mixed string doesn't take very long, so we can do that synchronously. And what we get back from thenApply is another completable future in this chain of completable futures. And we use that to go ahead and print the result. So this is similar to what we looked at yesterday, with the main difference being that yesterday we could run everything in the main thread. In this case, we're always starting up our completable futures running in a background thread. But otherwise, very, very similar. Let's go take a look at another variant of this. This is something we could have done yesterday, but we didn't quite do it that way, but we could have done it that way. But it would have been more ceremony, more extra work to be done. And this is called test fraction reduce async. So what we do here, same set of suppliers and big fraction and functions and consumers and so on. The difference is here, after doing supply async, which arranges to do the big fraction reduction in a background thread in the common fork join pool, we're now going to use thenApplyAsync instead of thenApply. So up here, before we done thenApply and then accept, and down here we do thenApplyAsync and then acceptAsync. And what happens there is that these actions are then typically run in a different thread in the common fork join pool than the thread that just finished doing the reduction. Now, for this particular example, that's probably overkill because, let's be honest, converting to a mixed string is lightning fast and printing the result is lightning fast. So this code is actually probably slower than the code above because we're doing additional context switches and moving things between threads in the common fork join pool and so on. So it's not necessarily the right way to do it. I'm just showing you how you can do it. And that's one of the things that I really like about completable futures is it's absolutely drop dead easy to get the completable futures to run their actions in other threads in the common fork join pool. Whereas with Project Reactor, as we saw, you have to kind of be explicit about where you want things to run if they don't run in whatever thread they were in before. So completable futures gives you a bit more control over that. But otherwise, very, very, very similar. Here's another fun example. This is something you strangely can't really do with Project Reactor. What we're going to do here is we're going to make a new completable future that starts out to be empty. And what I mean by that is that there's no computation associated with it or no value associated with it. So what we're going to do is we're then going to go ahead and spawn a thread, and we're going to have that thread go ahead and do some operation. In this case, it's very simple. It's just joining with the big reduced fraction future. So that'll be split second return. And we say complete on this. And what complete does is that's an indication to any other threads that are trying to join with that future that the computation has completed and the result is now available. So this is basically sort of a dynamic, lazy assignment to a completable future that was otherwise uncompleted up to that point. And then this thread will then continue on its merry way after the complete method is called. And notice that this thread here, the calling thread, could have gone off and done some other stuff for a while if it so chose. So this isn't a particularly good example because this code is so quick. It's like, what's the point of having a thread, right? So let's take a look at a more interesting example. And this example is going to also make an empty completable future, one that's not completed and has no computation associated with it yet. And then we're going to go ahead and make another thread, and we're going to go ahead and start that thread. And that thread is going to do a much longer computation. It's going to create big fractions, reduce big fractions from SF1 and SF2, which are nice big fractions. And then we're going to go ahead and multiply those things together. And then when we're done, we store the value in the future by calling the complete method. And that completes the transaction, if you will. It updates the future. So that runs longer, so there's more of a benefit for doing that in the background. And again, in a real program, we would probably do something interesting here. I don't really do much other than just call join. But in a real program, you would probably do some other things. So that's just kind of illustrating how you can take uncompleted or empty completable futures and connect them with more primitive Java concurrency mechanisms like threads and have them all work together in a very convenient way. Now, having said all of that, you're probably not going to use the APIs I just showed you a whole lot. Instead, you're much more likely to use the various factor methods like run async or supply async to do these kinds of things. We're going to spend the bulk of our time showing supply async because it's really the workhorse of completable futures. But I wanted to at least show you run async just for kicks. So here's run async. The difference between run async and supply async is that run async doesn't return a value. So it's basically a completable future to void. So there's no way to get the results directly. So in that particular case, here's an example where we kind of need to use an empty completable future called run async, which will schedule this supplier lambda to run in the background in the common fork join pool. And then when we're done, really the only way to get the result back is to complete that future. So similar basic idea as we saw before, just a little bit different mechanism because we're not creating a Java thread. Instead, we're using run async, which uses the common fork join pool. Here's yet another variant of this, just to show you all the many different ways you can use completable futures. This particular approach actually just uses a good old future, doesn't use a completable future at all. What it does is it makes a callable, which does the big fraction multiplication, and it goes ahead and it submits that callable to the common fork join pool, and we get a future back for it, and then we can say future.get. So this is really even more old school. This is the Java 5 level future mechanism integrated with the common fork join pool. One of the great things about completable futures is you probably never need to use classic Java futures again, and that's a good thing. Classic Java futures are really wonky and limited and kind of suck. So now let's get to a more effective way of doing this stuff. This is more, everything I showed you up to this point has largely just been sort of background information. Now let's kind of take a look at what people are most likely to do in practice. So test fraction multiplication supply async. This is the more canonical way of doing completable futures. What we do is we create a supplier lambda and we say completable future supply async, and we pass in that supplier lambda, which in this case is going to multiply two big fractions. And the value here gets stored as a completable future to a big fraction. So this has now been launched. It's running in the background. We can go off and do whatever it is we want. And then when we really, really need the result, we can call join. Join is very much like block in the Reactor project or blocking get in RxJava. Much the same kind of idea. It causes the thread to wait. And as a general rule of thumb, you want to avoid or minimize that as much as you possibly can. All right. So there's yet another kind of interesting enhancement to completable futures that was added in Java, I think it was Java 9 and beyond. And it was something that's called completeAsync. So you saw before that we had the complete method. So up here you saw complete. And complete is a synchronous call. So it goes ahead and this computation here will run, we get the result, and it gets stored in complete. But the computation here is a blocking computation. CompleteAsync is the same kind of idea. You're trying to set the value of the future, but we're going to do it asynchronously. And it is devilishly hard to find examples of using completeAsync. It was like a feature that was added to Java 9, and nobody ever really stopped to think about why they were going to document what it did or demonstrate how it works. But here's an example just to illustrate how it works. So we make ourselves a completable future, and then we go ahead and we attach a runnable to that completable future. And this runnable, in this case, is just going to say, completable async result equals, so it just puts a string here. So we've attached this runnable to the string, and then we call completeAsync. And what completeAsync does is it goes ahead and it runs this computation here in the background. So rather than up here where we did this computation, let's go find it with complete, right? We ran this computation, we had to do a run async, or we had to do a thread, right? If we wanted it to run asynchronously. In the completeAsync model, all you need to do is basically say, give a lambda supplier, and that will then go off and run in the background. But the first thing that's going to happen is all of the runnables that have been attached to the future are going to get run. And again, I really don't understand the rationale behind this method, but this is an illustration of how to use it. So down here, we can go ahead and join with that completable future. That will then wait until this computation is done and until this computation is done. And I'd have to run this and look carefully to see exactly how this works, but it's my recollection that then run is called in the calling thread, and the completeAsync is called in a thread from the common fork join pool. I think there's also a then run async if you want to get things off the user interface thread. So these are just, I think, rather esoteric features of completable future, but I'm showing you how they work because I could never find good examples of them online. All right, so those are kind of the basic mechanisms of completable future. Now let's talk about some more interesting mechanisms. And you'll very quickly see the synergy between what I'm showing you here and the various examples we looked at yesterday with respect to Project Reactor, which is also very similar to RxJava in this respect. So here we're going to go ahead and combine fractions together. So we're going to make a random number generator, and then we're going to go ahead and asynchronously generate a very large big fraction that will be, I guess we should actually say true here. It probably needs to be reduced. And then we're going to go ahead and multiply that random reduced big fraction with the S big reduced fraction. That's that constant that we defined way earlier as a field. So these computations, making the big fraction and multiplying this big fraction, they're all going to go on in the background in a common fork join pool thread. And we get back something we call CF2 here. And CF2 is just a completable future to an ongoing, long-running computation of big fraction. Then we go down here and we do the same thing. We go ahead and make another different random big fraction, and we multiply that also. So both of these supply async calls are now running asynchronously in the background. And what we're going to do is we're going to go ahead and create another consumer called mixed fraction printer, which will just be used to display the results. And then we go ahead and we use the thenCombine method. And what thenCombine does, much like the zip width method we looked at for Project Reactor, which I think is very similar to the zip method that's part of RxJava, it goes ahead and takes two completable futures that are in the process of running in the background, and it says, when both of those futures complete successfully, then go ahead and apply this particular action, which in this case is just adding the results of the two big futures, big fractions together. So that's what thenCombine does. And notice that that's entirely asynchronous, right? So we start the wheels in motion, things are running asynchronously, we leave a placeholder for combining them later when they finish, but that doesn't block either. And then we go ahead and register this action, and then we go ahead and call then accept, and after the combination is done at some point in the future, after these asynchronous calls complete, then we go ahead and print the results as a mixed fraction. And you'll notice that this particular example returns a completable future to void as the return type, and then that's weighted upon by the async tester. So that actually won't complete until all this long-term, long-running computation comes to an end. And if you take a look at the computations here, you can actually see that test fraction combined takes a long time to run. It's a very large, big fraction, and we're doing these reductions and multiplications. So it just takes a long time to run to get it all done. Okay, so the next thing I want to show you here are really some of the more interesting examples of completable futures, because they demonstrate how exception handling works. And as it turns out, there's quite a bit of expressivity available in completable futures to handle exceptions. Arguably more expressive ways of doing it than with Project Reactor or RxJava. So let's take a look at the code. And it's kind of fun to go back and compare and contrast this code with the Project Reactor code we looked at yesterday, because there's similarities and differences. So what we do here is we're going to make a list of Boolean values, true and false. We convert that into a stream of Booleans. We then map that, and we use the true and false as a flag to indicate whether or not we should be dividing by 0. And the way this works is we call completable future supply async, and we're going to go ahead and create a big fraction that has a numerator of 100 and a denominator of either 0 or 1. Obviously, if it's 1, everything's cool. If it's 0, we're going to get the arithmetic expression, arithmetic exception. So what happens here is that we're then going to connect the output of supply async, which is, of course, a completable future, with the .handle completion stage exception handling method. And what this does is you get 2 parameters passed in. One is the actual value. If we were successful, it'll have a non-null value. And the other is the exception, which, if an exception occurs, will be a non-null value. And those 2 values are mutually exclusive. So you can't both have a valid value, i.e. fraction non-null, and an exception, which would be EX non-null. One of them has to be non-null, and the other has to be null. So if the fraction is null, that means we got an exception. So in that case, we go ahead and note the exception, and then we just return this as a 0. So handle is quite a bit like on error resume from Project Reactor, much the same kind of idea. So we can do something with the exception, and then we can keep going by giving back a new value. And then if we didn't get an exception, we multiply the fraction that's been reduced by the big fraction, big reduced fraction constant. And then out of handle will either come that multiplied reduced big fraction or 0, in which case we go ahead and accept the results, and then we print the results as a mixed string. So what we're doing here is we're basically going to have a stream which will end up being, as you can see here, completable futures to void. So we have a stream of completable futures to void, which we then go ahead and collect using our good old futures collector like we always do. I love the futures collector. It's one of my favorite things about completable futures. And we then take that, and when we're all finished, we then compose the result, which is just an excuse to have a hook to print the result, and then we return the S-completed completable future that's been completed with a null. And that's just a way to say, hey, async tester, we're all finished. You don't have to wait for us anymore. So that's basically one exception handling model, and that's using the handle method. Let's take a look at another model. Everything's the same. The difference here is that rather than using handle, we're going to use the exceptionally completion stage exception handling method. And as you can see here, the way this works is if you go ahead and do a supply async on a big fraction that has a 0 denominator, then an exception is thrown, and it skips over all the completion stage methods until it finds an exceptionally completion stage method. And that's what handles the exception. So that's a little bit like a try-catch block in synchronous Java, where when an exception occurs, control transfers to the appropriate catch clause in the catch part of the try-catch block. So that's kind of what's going on here. On the other hand, if we have a denominator of 1, then the big fraction will have the value of 100. We apply the multiplication action here, and then we skip over the exceptionally part. So exceptionally only gets called if there's an exception, and if it's not an exception, it's skipped. Likewise, all these intermediate completion stage methods are called if there's no exception, but if there is an exception, they get skipped. And then the final thing we do here is we do a then accept, and we end up with a stream of completable futures to void, which we then collect into a single completable future, and then compose on. Okay, so that's another way of handling exceptions. Here's a third way of handling exceptions, and this is sort of a variant of both earlier approaches, the handle approach and the exceptionally approach. And the method it uses is a very interesting completion stage method called whenComplete, which can be used for exception reporting, as we do here, and it can also be used for other purposes as well. whenComplete is kind of an all-purpose hook that always gets called whenever something completes, even if an exception is thrown. So that's the way to think about it. It's kind of like a always called hook, if you will. So take a look here, same idea. We have our list of true and false. We turn it to a stream. We map it. It might throw an exception. If there's an exception thrown, then apply gets skipped. But whenComplete always gets called. And so what whenComplete does is it takes the fraction and the exception, and then it checks to see which one is non-null. So if the fraction is non-null, that means we succeeded. So we're going to go ahead and print this as a mixed string. Otherwise, if the exception is non-null, we could say if ex not equal null. The reason we don't actually have to test for that is that there is no way on the face of this wonderful green earth that you're going to have fraction be null and ex be null. That should never happen. But if you're really paranoid, I guess you could test for it. So in that case, we're just going to go ahead and append the exception message. whenComplete is actually not an exception handling method. It doesn't swallow the exception. So if we don't do anything else, the exception will be propagated out of this chain of completion stage methods and end up somewhere else. So what we do here is we go ahead and just swallow the exception. We could have put that elsewhere, but I like to put it at the end of the chain just to indicate that it's not doing anything other than just swallowing the exception. As before, we collect to a future and then compose. Just a couple methods left to go through here, and then we'll take some questions. So this particular approach is really cool. This shows off the test fraction multiplications 1 method. And this is similar to the test fraction multiplications multiplications 1 method we looked at yesterday for Project Reactor. But of course, it uses the streams and completable futures framework as opposed to using the flux mechanisms in Project Reactor. A lot of it looks very similar, though. So we start out by making ourselves a big fraction and completable future to big fraction function called reduce and multiply fraction, which will go ahead and perform the reduction asynchronously using supplyAsync. And then we go ahead and do a then compose. And we, in this particular case, we're going to go ahead and do the another multiplication. We're going to do the multiplication asynchronously as well. So we're going to do the reduction asynchronously, and then we're going to go ahead and we're going to do the multiplication of the reduced fraction asynchronously, and we're going to compose the results together so we end up with a completable future to a big fraction. If we don't use then compose here, we try to use then apply, we're going to have this be completable future to big fraction, which is a bit wordy. Another thing we could do here, by the way, and I'm just going to show you this because it's important to know this idiom, we could have gotten rid of this code and instead said, then apply async. And in that particular case, what we would do is we would say, reduce fraction. So then apply async is kind of a shorthand way of doing then compose on a nested supplyAsync. And in fact, I actually kind of like the then apply async idiom a little better. So I think I'll leave my code like that. But the point is that they're kind of mirrors of each other. You can either do a supplyAsync and then compose it, or just do then apply async. There are some situations where they're not equivalent, but in this particular case, they're equivalent. And in both cases, they'd end up running this multiplication in some other thread in the common fork join pool. Now what we're going to do is we're going to have a stream. So now we're combining Java sequential streams with completable futures. We're going to generate an endless stream of big fractions that are random and unreduced. And then we're going to limit that to just S max fractions of them. This is very much like what we did yesterday with our Project Reactor approach. Then we're going to go ahead and reduce and multiply everything. So for each of those large unreduced big fractions, we're going to go ahead and use map. And map is going to call reduce and multiply fraction. And reduce and multiply fraction, as you recall, is going to do a whole bunch of asynchronous processing. So basically, for every one of the unreduced random big fractions, it's going to get reduced and multiplied in a thread in the common fork join pool. So there's a lot of concurrency going on at this point. Lots of things are running in the background asynchronously. And that comes back, as you can see, as a stream of completable futures to big fractions. We use our futures collector to turn that to a completable future, to a list of big fractions. And when they're all done, and this is going to take a while, and in fact, if you look at the output, these big fractions are absolutely gigantic. Look at this. I'm still going, right? I'm going and going and going and going. These are really, really large numbers, so they take a long time to compute. When they're finally done, that one future will trigger, and then the thenCompose method will be called, and we'll go ahead and call sort and print list. And sort and print list, as you might expect, is the same trick we used the other day with the Project Reactor code, where we're going to go ahead and do a quick sort, and we're going to do a heap sort, and we're going to do them both in parallel, and then we're going to use another advanced completable future mechanism called acceptEither, which will just take whoever finishes first, the heap sort or the quick sort, and then we go ahead and print the results. And that, of course, is what you see if you take a look here. That's the results that are printed in sorted order. So same basic kind of trick that we saw the other day. Okay, let me just pop back up here and we'll take a look at test fraction multiplications 2. Oh, I see what I did. I got ahead of myself here. So this particular approach, I guess I should remember this for the future. This particular approach used the version, the variant here that used thenCompose and supplyAsync, and this approach down here used the approach that used thenApplyAsync. I just got ahead of myself. So this approach is doing the same thing, it's just using thenApplyAsync as opposed to thenCompose and supplyAsync. But otherwise, it's basically more or less the same code. Okay, so hopefully that was helpful. The key points to take away from this, I think the key points to take away from this are that you can do pretty much the same things with completable futures as you can with Project Reactor and RxJava. For my particular taste, I think the completable futures API is a bit more expressive and a little clearer, and it makes it easier to do certain kinds of asynchronous processing without having to do all kinds of funky little wrappers like the Reactor util stuff I showed you, where we're doing, transform deferreds under the hood and playing all these games with those mechanisms. So it's more straightforward to write concurrent code. But of course, the other difference is that Project Reactor, like RxJava, also combines the sort of streams and parallel streams like approaches. So they're really doing kind of two paradigms. It's kind of reactive streams, right? Whereas with Java, streams are streams, and async, the completable future stuff, is kind of reactive. And then if you want them, you can combine them, as we've shown here, but they're really kind of described in more independent terms in the classic Java documentation for modern Java. So that's, you have to know both frameworks to combine them, whereas with Project Reactor or with RxJava, it's all part and parcel of that one framework. And there's, of course, pros and cons each different way. So with that, let's go ahead and take some questions. And let's see if I can make my screen big and then talk about the question. Okay. So what does it mean that the common fork join pool is shared across applications? So if you take a look at the common fork join pool, this is certainly true for Java parallel streams, but it's true in general. If you have an application, well, let me rephrase that. If you have a process, right? You have a process that contains multiple different applications or different capabilities, if you will. Maybe just different streams for that matter, different parallel streams. They're all going to share the same common fork join pool within that process. Now, if you have, 5 processes running on your computer, each running its own virtual machine, then they'll each have their own common fork join pool, and they don't conflict with each other directly, although they will compete for the same set of cores. But let's ignore that case. Let's just talk about the case where we have multiple parallel streams or multiple applications in a common process in Java. All that means is that all the different computations that are running in a parallel stream or using the completable futures with the default common fork join pool, or using common fork join pool just for other purposes, they all share the same common fork join pool. And that's by design. And there's actually a very good reason for doing that. And the good reason for doing that is if the whole concept of common fork join pool is to be able to do effective work stealing. And the purpose of work stealing is to try to maximize utilization of the available cores. So if you have one common pool and all the work gets dumped into that one common pool is able to do maximally optimized work stealing of all the different tasks it has running in the various decks or queued up in the various decks, double-ended queues, in the worker threads in that common fork join pool. So that's why they do that. That's why they have it like that. Now, there are some situations where you don't want to do that, where you might want to have different pools that are separated from each other for various purposes. Maybe one pool runs at a different priority than the other pool. The threads in a pool run at different priorities than the threads in another pool. So in that case, you might want to differentiate the pools. Completable futures makes that very easy to do because you can pass in an executor parameter to supply async or to run async, and then that'll be used as the place to run the computations for that particular chain of asynchronous computations off of the initial supply async or run async calls. So there's flexibility with that. With parallel streams, you can do that, but it's kind of a hack, and people are discouraged from doing it because it's not guaranteed to be portable across new releases of the Java platform. So that's what it means. How is complete async different from supply async? So keep in mind, supply async is what sets things in motion to schedule the initial computation to run in a common fork join, in whatever fork join pool you want to use or whatever thread pool you want to use. And from that point onwards, you can then chain a bunch of completion stage methods off of the completable future returned by the supply async method to chain together that processing in a nice fluent manner. In contrast, complete async comes at the very, very, very end. So complete async doesn't give you back something that you can chain together. I think it gives back a void or something like that. So it's really intended just to run that one operation asynchronously and get its result and then store it as the result of the future. But you can't chain together a bunch of things the way you would do with supply async. I honestly have not found a lot of good examples of complete async to give as motivating examples for it. So something tells me that the people from the Java development team didn't think of a lot of examples either, because there don't seem to be any tutorials or online examples that show it in any meaningful way. Another question, does the handle completion stage API, which is one of the ways of handling exceptions, does it handle exceptions for the entire pipeline or only for the calling completable future? So you can basically, it'll handle it from the point before up to that point. And then, of course, if you return something which will be a completable future and continue on down, some other completion stage method later on in the chain could also throw an exception. And then that could then be handled by subsequent calls to handle. So it's not one handle per chain. It's basically kind of the chain of responsibility pattern from the Gang of Four book. It'll kind of search so it finds that handler that'll handle it. Then it keeps it going down the chain. If another exception occurs in some later completion stage method, some later handle method could be used to catch it, and so on. So yes, you can handle the exception and resume the next operation of the pipeline. That's correct. And in RxJava Reactor, do we have anything similar to Managed Blocker? Why, yes, you do. In fact, it's so similar, it's Managed Blocker. So one of the great things about the Managed Blocker mechanism, as well as one of the great things, or two of the great things about RxJava and Project Reactor, is that they allow you to be able to select the thread pool where your operations run. And because you can do that through doing things like subscribe on or publish on or observe on or run on, all these good things, you can designate where you want the computations to run. And you can select the common fork join pool. And in fact, if you look at the bulk of the examples I've shown you so far, I've pretty much always used the common fork join pool. Didn't have to, I just chose to do that. So the cool part is that you can choose to use the common fork join pool. And then when you choose to use the common fork join pool, you can use all the managed blocker stuff. And in fact, if you go back and watch some of the very first videos I did from the first week or so, I show some examples. And in fact, we're going to look at that particular example tomorrow, I think, because we're going to revisit it and then focus more on parallelism and support for parallelism in Project Reactor, looking at parallel fluxes. So that'll give us a chance to talk more about this. But yes, there's nothing wrong with combining the managed blocker mechanism that comes out of the box with Java 8, and I think it might even have been in Java 7. I take it back. I think the common fork join pool came in Java 8. So Java 8's mechanisms for managed blocker can be applied quite nicely in the context of using either RxJava or Project Reactor. And tomorrow we're actually going to see how to make that work. Yeah, so those are all really good questions. So what I think I'll do here is just switch back over to my screen sharing for a second and show you what I think we're going to cover tomorrow. So in tomorrow's lesson, we're going to return to we're going to go back and look at these interesting examples that we've covered before. And this particular one happens to be in the RxJava folder, but really, as you'll see, I've extended and enhanced it. So what we're going to look at is this version of, I think it's this one. Let me take, yes, this is the right one. So in my RxJava EX2 folder, which I've updated recently, I've now created and separated out the streams examples, the RxJava examples, and the Reactor examples. And what these things are going to be doing is they're going to be downloading but basically just downloading large images from my website. And they're going to show off all these different mechanisms. Now, we've looked at this example before, so we're going to skip over a lot of the stream stuff and so on. And instead, what we're going to do is we're going to be focusing primarily on Project Reactor variants of this stuff. And the Project Reactor variants of this stuff are cool, and I'm going to show you a bunch of different variants of the Project Reactor implementation. So we're going to take a look at how you can set the parallelism level. We're going to take a look at what happens if you set it too low, what the implications are. We're just going to play around with it. And I may also throw in some additional discussion of parallelism with parallel fluxes, which is very similar, by the way, to the mechanisms that are available with parallel flowables in RxJava. But I've decided I like the Reactor way of doing things better than the RxJava way of doing things. So I'm focusing my attention more on that. But these are very, very interchangeable features. So you can kind of mix and match as you see fit. So that's what we're going to cover tomorrow. As always, I really appreciate everybody coming and asking questions. And I've still got a bunch of ideas of things to cover in the future. So we'll keep doing this probably at least another week. And at some point, I'm going to have to stop and rebuild my arsenal of knowledge to teach from. But right now, I still got a whole bunch of stuff, and I'm still having tremendously good time learning all this RxJava stuff and Reactor stuff. And maybe at some point, hopefully too, we can show some discussions of combining Project Reactor with WebFlux, which is this really cool reactive web microservices environment that's part of the Spring project. Okay, so that's pretty much what I wanted to cover today. I look forward to seeing you soon. And if you have any questions or comments, please don't hesitate to post them somewhere, and I'll be happy to respond.